this. Everything is okay.
Okay,
Perfect, thanks.
great. Great. So, thank you very much, of course, for the prize to Professor Sceldi Ambrosi, who is the editor-in-chief of the Revista dell'Unión Matemática Argentina, to Ursula Molter, the president of the Unión Matemática Argentina. And as Adriano already said, it has been really a pleasure for us to receive this award. I mean, and thanks also to the other members of the committee. So, in order to begin, I will present these results, and I will start from the very beginning. I will make a presentation with many information in the first part, since it's easier to understand which are the problems we want to deal with. So let's start with the very simplest case, to start with real and complex vector spaces. And in fact, what is a complex vector space? Well, a complex vector space is nothing but a real vector space endowed with an extra structure, which is exactly multiplication by the imaginary unit, which is encoded by an endomorphism of this vector space, whose square is minus the identity. And these two languages are essentially the same, but of course, speaking of complex vector spaces is an intrinsic description of the subject, while in the second way of describing them, one wants to to stress the relation between real and complex aspects. This can be useful. For example, it might be recalled that if we start from a complex vector space and we see it as a real vector space with the almost complex structure I, then once we choose a C basis, a basis on the complex numbers for this space, then we can produce in a standard way, namely applying I, the almost complex structure, to all these vectors, a new basis over the reals, and so we can have an orientation on the vector space V, which has the properties that it doesn't change if we change the C basis we start with. So it's something which is intrinsic of the complex vector space, but to highlight it, this real approach is convenient. What we can do also is to take the complexification of the real vector space V, namely tensor it with C, extend scalars to the complex numbers, and then we can have a decomposition we call it into type 1, 0 and 0, 1, where these two subspaces of the complexification of VC are the eigenspaces relative to the imaginary unit or minus the imaginary unit of the C-linear extension of the almost complex structure. Moreover, with this description, in fact, we can recover our original space V with its complex structure induced by I, simply as it is the 1, 0 part of this decomposition. This decomposition has the effect that also the exterior powers can be split into some of space called the VPQ. The definition of VPQ is the one you can see in the presentation, is the wedge product P times of V10 and of Q times of V01. And this gives rise to the so-called type decomposition of the kth exterior power of VC. Of course, once we have an almost complex structure I on a space, it's canonically induced on its dual space, another almost complex structure, with the properties that the 1, 0 part essentially is the set of all the functional whose kernel contains the 0, 1 part. And finally, that it commutes, the B degree, the composition commutes with taking the dual. Now, what we can do once we have a vector space is to add a metric on it and to study if the metric is compatible in some sense with the almost complex structure. The easiest way that they may be compatible is that the almost complex structure, as an endomorphism of V, is orthogonal with respect to the metric, to the inner product G. And if this is the case, we can produce it in a very standard way to form this form called omega, which is G, where the first entry is twisted by I. We computed not G of VW, but G of IVW, which turns out to be of type 1,1 with respect to the type decomposition induced by the almost complex structure I. And then once we have omega, we can induce a Hermitian metric on the complex vector space VI, which is the one you can see. And in fact, two of the three data, I, G, and omega, uniquely determines the third one. So once we have this 1-1 form, we can use it to define the wedge product with it. And this is the so-called Lefschetz operator, which is a real operator on the exterior algebra of the complexified vector space. And it has the effect that with respect to the type decomposition, it raises both indices, the type, by one. So it sends PQ forms to P plus 1, Q plus 1 forms, since, of course, omega is of type 1, 1. Moreover, as we recalled, since V has a natural orientation, we can use this orientation to define the so-called Hodge star operator via the relation you can see in the slide, simply requiring that star alpha, where alpha is a K form, is the only form such that beta wedge, the conjugate of star alpha, is equal to a suitable multiple of the volume, and this multiple is nothing but the Hermitian extension of G evaluated in beta and alpha. If we require that this holds for every beta, then we are basically defining the star operator. And here is important that vol is the natural orientation induced by I, which I recalled before. Now, with these two operators, we can give to the adjoint of L with respect to the Hermitian extension of G, a particularly simple expression, since, of course, theoretically, this dual operator or adjoint operator lambda is well defined, but to find an expression of it, it might be difficult. In fact, it's not the case, since lambda is nothing but the conjugate of L, of the Lefschetz operator, with respect to these Hodge star operators. And once we have these three operators, we can define primitive elements and the primitive decomposition of the exterior algebra. So an element in the exterior algebra of the complexified vector space VC is said to be primitive if it's annihilated by lambda, and we denote by pk the set of k forms which are primitive. What is possible to show is that, in fact, pk is trivial if k is big enough. Now, I've not stressed it in the beginning, but n is the complex dimension of V, which is half of the real dimension. So, in fact, VC, the complexification has dimension 2n, and this n is the complex dimension of V. While for k small, less than or equal to n, actually we can compute the set of primitive forms as the one which are annihilated not by lambda, but by a suitable power of the Lefschetz operator itself. Finally, Here, this is a big result in some sense, but for every k, we have a direct sum decomposition of the space of k forms in terms of powers, yes, of the Lefschetz operator applied to primitive forms. This essentially says that every k-form can be written as a sum of powers of omega wedged with primitive forms of the appropriate degree. Now, L and lambda, being real operators, are compatible with the decomposition into type, so we can also speak of primitive forms of type 1, 0, 0, 1, PQ in general. And let's see what happens in the low-dimensional cases. So k equals 0, there is nothing to say, everything reduces to C. For k equal to 1, we know that our vector space VC splits, V star, C splits into the 1, 0 and the 0, 1 part, and these are all made by primitive forms, and so there is very, very few to say also in this case. What happens for k equal 2? For k equal 2, we have that two forms, in principle, are the sum of forms of three types, the one of type 2, 0, of type 1, 1, and of type 0, 2. Now, type 2, 0 and 0, 2 forms are for sure primitive, since if we apply lambda to a 2, 0 form, for example, we should end up with a 1 minus 1 form. And there are none of them since minus 1 is negative. So this tells us that lambda on a 2, 0 form is trivially trivial, and that every 2, 0 form is actually primitive. On the contrary, in the 1, 1 part, there is something. So the Lefschetz decomposition says that we have P1, 1, so the primitive 1, 1 forms, plus L times omega times something which is a 0, 0 form. So it's a complex number in this case. And we have this decomposition of the 1, 1 part. As usual, now we have something which is on a vector space. To have the corresponding picture in geometry is to try to use vector bundles. So what we can do, if we have a compact complex manifold, we can look at its real tangent bundle, and the multiplication by minus 1 on each fiber, so on each tangent bundle, defines an almost complex structure, and all these almost complex structures glues together to give a vector bundle morphism whose square is minus the identity. So we can apply, as I'm writing here, a sort of bundled version of what we did before. Everything we made pointwise can be glued together to give something which holds at the vector bundle level. And in particular, we can have a decomposition of the cotangent bundle, of the complexified cotangent bundles into type 1, 0 and 0, 1, where the type 1, 0 forms is nothing but, the part of type 1, 0 is nothing but the usual holomorphic cotangent bundle of the complex manifold. And so we have also a direct sum decomposition for all the bundles. So the bundle of K forms can be decomposed into the sum of the bundles of PQ forms. What happens is that since we are starting with a complex manifold, if we take a form of type 1, 0 and compute its differential, then this differential splits into two parts, the part of type 2, 0 and the part of type 1, 1. We have a dual picture for what happens in type 0, 1. So the differential of a 0, 1 form splits as the sum of a 1, 1 part and the 0, 2 part. And since locally each PQ form can be written as the wedge product of 1, 0 and 0, 1 forms, this gives rise to a decomposition of the exterior differential, so that this splits as the sum of these two operators, del and del bar, which on the bundle of PQ forms are nothing but that the projection into the part of type P plus 1Q and the PQ plus 1 respectively of the differential. Now, since this d squares to 0, we deduce these relations, namely that both del and del bar square to 0, and that del and del bar commute, anti-commute with each other. And this allows us, as we were saying before, that to define the Dolbeau cohomology of a compact complex manifold. Namely, if we take the complex of P dot forms, this is a complex with respect to del bar, and its usual cohomology gives rise to the PQ cohomology group or Dolbeau cohomology group with respect to del bar. And the same holds if instead we look at the operator del, so that we can define these two spaces of forms. As we did before, now we introduce a metric. If to introduce the metric must be, the Riemannian metric we are considering must be compatible in the sense that, of course, must be orthogonal with respect to G, and we can define the fundamental form for this metric. And then all what we saw before, so the Lefschetz operator, the Hodge operator, the adjoint operator of the Lefschetz operator, can be promoted to bundle operators, which will have the same name, L, star, and lambda. And so we get, in particular, a primitive decomposition at the level of bundles. So the bundle of K forms splits into the sum of Li applied to the bundles of primitive forms, and the same and the similar decomposition holds when we are looking at the B-degree decomposition, so forms of type PQ. We have now, with respect to what we were saying before, the complex space, the vector space case, we have now something more. We have the geometry which is essentially encoded into the differential. So if we ask the metric, the complex structure, and the geometry itself of the complex structure itself to interact with each other in an appropriate way, we can get something more. The requirement we make, what we usually do, is to consider Kähler manifold, which are the one for which the fundamental form omega of G is closed. And in this case, these are classical results. What happens is that the decomposition we had before for bundles descends to cohomology. So we have a Hodge decomposition of the RAM cohomology, and we will have also the composition of the RAM cohomology with respect to the primitive cohomology. Okay. Moreover, it must be recalled that on compact Kähler manifolds, the spaces of the Dolbeau cohomology, the spaces of Dolbeau cohomology coincide. So there is no difference to compute the one with the del and the one with the del bar. In fact, what happens is that the kth, the RAM cohomology group, splits as the sum of the Dolbeau cohomologies, where the B-degree PQ is such that P plus Q is equal to K to the degree we are considering. And this decomposition does not depend on the chosen Kähler metric. More difficult is to give the Lefschetz decomposition, but again, it is possible to do it. On a compact Kähler manifold, the kth, the RAM cohomology space, splits as the sum of Li, the Lefschetz operator, applied to suitable spaces of primitive cohomology. In fact, it's possible to show that lambda commutes with the differential, so that it descends to give an operator lambda on the cohomology, and so it makes sense to define primitive cohomology classes. what makes everything work, about what we were saying before, it's not just the fact that we are introducing the Kähler condition, so that omega is closed, but actually that we were dealing with a complex manifold. And if you think at what I was saying before, it may seem that a complex manifold is nothing but a real manifold whose tangent space is endowed, whose tangent bundle is endowed with this morphism whose square is -1. But this is not the case. In fact, the key point was that the differential splits as the sum of del and del bar, which was due to the fact that the differential of 1, 0 forms is just given by 2, 0 and 1, 1 components. So there is no component of type 0, 2, which in principle is allowed. In fact, if we simply consider real manifold with an almost complex structure, then this almost complex structure is induced by a complex manifold structure. So we have an atlas with complex charts whose transition functions are holomorphic, if and only if we have this decomposition of the differential on 1, 0 forms, or equivalently if del bar squares to 0. And this is dramatic for the theory, since we want, if we want to deal with almost complex manifolds, not necessarily complex manifolds, then we must deal to the problem that D now splits into the sum of four parts, not just two. We have del and del bar as before, but then this mu and mu bar appears, which have this strange, uh, strange, well, at first it seems strange behavior on the B degree. It raises P by 2 and lower Q by 1. And then we have also that the relation d squared equal to 0 now gives us more equations. For example, let's read the last line. Mu bar squares to 0, mu bar and del bar anticommutes, and then we have this relation with which involves del bar squared. Now, the fact that on a genuine almost complex manifold, del bar does not square to 0 is a problem, since if we want to introduce the Dolbeault cohomology, uh, simply we cannot do it with del bar. It does not define a cohomology. Recently, to deal with this problem, Cirici and Wilson proposed a different approach to generalize Dolbeault cohomology to almost complex manifolds. And we will use all the three properties of the last line in this slide. So as mu bar squares to 0, the first thing we can do is use it to compute a mu bar cohomology. So it's the kernel of mu bar over the image of mu bar, as usual. But then, since mu bar and del bar anticommutes, we have that del bar descends to the mu bar cohomology, inducing a map, which we called as usual, simply del bar. And what happens is that because of the last relation, on the mu bar cohomology, del bar squares to 0. So now it is a differential, and we can finally define the Dolbeault cohomology of an almost complex manifold as the kernel of this del bar over the image of this del bar. So it is something involved. It's not so natural. Of course, if we are starting with a complex manifold, we recover the usual Dolbeault cohomology. And the problem is that this definition has some problem. In fact, they computed that, for example, in some compact example, it may be infinite dimensional. So it behaves very differently in the almost complex case with respect to the complex one. So maybe one can try something different. And here, a different approach can be the one using harmonic forms. since if we now introduce the metric G, a Riemannian metric which is compatible with the almost complex structure I, so that it's a Hermitian metric. We have the fundamental form of omega, we have a bunch of operators. Well, we can give an expression to the adjoint operators for d, mu, del bar, mu bar, which in terms can be expressed in terms of the star operator, and introduce the Laplacian. The Laplace operator associated to d, to del, mu, and so on. All the forms which are annihilated by the Laplacian are called harmonic forms. So we have harmonic K forms if we are dealing with the differential D, the exterior differential. Or we can also look at the B-degree decomposition. We can speak of PQ harmonic forms. And here we have that since the Laplacians are elliptic differential operators, then the spaces of harmonic forms are finite dimensional for some general results on elliptic operators. Moreover, since every, let's say, d-bar harmonic form is actually also d-bar closed, we have a natural map from the space of PQ del bar harmonic forms into the PQth Dolbeault cohomology group with respect to del bar, the one sending the form to the class it represents. And it happens that on compact complex Hermitian manifolds, these are isomorphisms. So in the case where the almost complex structure is in fact a complex structure, we have a way to recover these vector spaces from analysis, from harmonic forms. In the case where the metric is scalar, we have something more. Basically, we have that the Laplacians associated with d, del, and del bar coincide. Well, actually, this is not true. As you can see, the Laplacian of del and the Laplacian of del bar, they do coincide, and they are multiple of the Laplacian of d. So in particular, the harmonic forms are the same, the kernel are the same. Now, the idea is then, if we want to study some decomposition and to see if it passes to cohomology, we are in trouble in the case of almost complex manifolds, since we have no way to define Dolbeault cohomology. What happens if we look instead of harmonic form? Is it possible to have splittings of harmonic forms which mimic the decomposition into type or the Lefschetz decomposition? Of course, if we are interested in these problems, the first case one is naturally led to consider is the case of almost scalar manifolds, namely the case where we have a compatibility of G, the metric I, the almost complex structure, and the complexes and the geometry itself of the manifold underlying requiring that the omega is equal to 0. What we lose here, of course, is that now I is not necessarily complex, but maybe only almost complex. So the first goal is to see if the decomposition, the Lefschetz decomposition of the types descends to d-harmonic forms. And this, in fact, is the case. As you can see, Chirich and Wilson proved some years ago that on an almost scalar manifold, then the PQ d-harmonic form splits as the direct sum of Li applied to the suitable space of primitive forms. So it's possible to write each PQ harmonic form as the sum of powers of omega wedged with the primitive harmonic forms of the correct degree. The natural question is, what happens to the operators del and del bar. And here we come to our, more specifically to our work. The simplest remark we can do is that if we look at P0 forms, then since when we apply lambda to a P0 form, we should end with a P minus one form, and there are none of them, then every P0 form is actually primitive, and the same holds for 0Q forms. And so this has as an immediate consequence that each P0 del or del bar harmonic form is actually primitive. So we get in this way the right decomposition. If we look now at the first, the lowest degrees, we have that 0, 0 is easy, 1, 0, and 0, 1 is in this proposition. Then we have 2, 0, 0, 2, which are again in this proposition. The first case of interest is what happens to 1, 1 harmonic forms. Sorry, yes, I forgot. Starting from this result, it follows almost directly by applying the Hodge star operators that we have similar decompositions for the space of n minus p. This means essentially that all the edges of the Hodge diamond of an almost complex manifold, what should be there, in fact, we have a primitive decomposition for all these spaces. What is great is that in the middle, so in degree n0 and 0n, we have also the equality of the spaces of harmonic forms. So n0 forms are del harmonic if and only if they are del bar harmonic, and the same holds for 0n forms. Great. What I was saying is that the first case of interest, in fact, is the case of 1-1 forms. And if we look at an almost scalar manifold, then in B degree 1, 1, it happens that 1, 1 forms admits Lefschetz decomposition as we want. So we have that the space of 1, 1 del bar harmonic form is in fact the sum of a part which is multiples of omega, the Kähler form, and the other part which is given by del bar primitive 1-1 forms. As a consequence, we can see that we have a similar decomposition with respect to the del harmonic forms. And also, applying the star operator, we can get the composition to the spaces of n-1, n-1 del or del bar harmonic forms. Here, what is interesting is that in the decomposition of del bar harmonic forms, we have that the decomposition is a power of, is a multiple of omega to the n-1, plus omega to the n-2 wedged not with a primitive 1-1 form, but del bar harmonic 1-1 form, but with a primitive del harmonic 1-1 form. Here, this is in some sense interesting, since is the effect of having applied the star operator. Now that we know this, we can ask what is about the behavior of the Laplacian in the almost scalar setting. We know that on compact Kähler manifolds, the Laplacian of del and del bar coincide. Is it true also in the almost complex, genuinely almost complex case? So the answer is not in general, is no in general. And what actually we did was to produce an example considering R6 with coordinates and divided it by the action of translation by the lattice Z6 to get the standard torus. Now, if we take a function on the torus, which depends only on the last coordinates, x3 and y3, we can define an almost complex structure, declaring the form you can see as a global coframe of 1-0 forms. This is enough to define the almost complex structure. We can define a suitable 1-1 form, which is the Keller form of an almost Keller metric on T. And then we see that, first of all, if we choose our function g such that this v bar 3 of g is different from 0, where v bar 3 is the conjugate of v3, v3 is part of the dual basis of phi 1, phi 2, phi 3, then it appears in the differential of phi 1 some component of type 0, 2. So the almost complex structure cannot be a complex structure. And moreover, we can compute that the form phi 1 wedge phi 2 bar is always del harmonic. On the contrary, its del bar depends on, again, on V3G. So if we choose G such that not only V3 bar G is not 0, but also V3G is different from 0, then we get an almost complex structure, which is not a complex structure, and the form which is harmonic with respect to del, and which is not harmonic with respect to del bar, since it will not be del bar closed, which is a necessary condition for being del bar harmonic. So we see that, in fact, the operators, the Laplacian of del and of del bar, are actually very, very different, since they have different kernels. It's not like the integrable case where we have the same spaces. Finally, we may ask what happens if we go to other cases and to look for primitive decomposition in different degrees, different than 1, 1. So let's move above in the Hodge diamond. In the Hodge diamond, we have now 3, 0, which has primitive decomposition as a 0, 3 because of our first proposition. Then we have 2, 1. Now, do we have primitive decomposition for 2-1 harmonic forms? Well, what we could show is that, in fact, this is not the case. Well, not always the case, since there are examples of compact almost scalar manifolds where the primitive decomposition, where what should be the primitive decomposition of the space of 2-1 harmonic form, in fact, does not fill the whole space, but just a proper subspace. And we could obtain an example of this phenomenon, considering an appropriate almost complex structure of the Iwasawa manifold, and defining an almost scalar metric on it, and then working a bit to find that there is something which is del bar harmonic of type 2-1, but which does not fit into the sum of the primitive 2-1 del bar harmonic forms plus a suitable multiple of a 1-0 del bar harmonic form. So this is actually what we could do. The basic idea, what I think is the crucial point of all this construction was, as we were saying before, moving from cohomology itself to another aspect, which is the harmonic forms. Harmonic forms, to define them, we need a deep interplay between more geometric objects. We need the metric, we need the complex structure, but then this seems to be a fruitful field where one can find something new in the almost complex case, which is what we actually were trying to do. And great, so I think this is all what I wanted to say to you today. And so thank you very much for your attention.
Thanks, Andrea. Marcos? Okay, so if no, thanks for the talk. Uh, Marcos is there or not?
Yes, I am.
Okay, okay.
Thank you.
Maybe you stop. Yes,
Yes.
we
We
have
had
a
a
lot
problem
of
with the computer, and I had to put mine outside because we heard everything double.
double. See, yes,
No
if you
problem.
have well,
Okay.
very nice that we have so many people. I'm very happy.
Okay.
Yes, I don't know if there are some questions in the question not not loud because some colleagues of mine are in Marburg and they are not they
Connected.
cannot they are muted, they cannot talk. I don't know if they have made some questions here in the no
In the chat, there are no.
in the chat. Yeah, in the chat. That is what I wanted to say. Well, thank you very much.
Okay. Andrea, I have a general question.
Yes.
Apart from the subject that okay, so even in the theorem or also in the question and the answer, always you assume that compact, almost complex manifold, Keller manifold. Okay, so this is always the case. So if you does not assume compact, this is not possible to obtain this kind of decomposition.
Well,
Or
I
it's
don't know
open
in
question.
general if it's the real problem is that when you have something which is not compact, you may end up with some space of harmonic forms which are not finite dimensional. So this is the real problem. Since we are then interested to compute them, maybe in some example, to compare them, to try to find some information on the geometry of our manifold from the knowledge of that number, let's say, it's important that that number is always finite. So the real reason why we want compactness is maybe in this, because of this aspect.
Okay.
It ensures the finite dimensionality of every space, of everything we are dealing with.
Yeah.
Okay, so because this result looks like a global result, but there is also the possibility to have local results. I mean, local property of the decomposition.
Well, maybe I
Sorry?
to my feeling, what is the local decomposition is the sort of bundled version, the decomposition with vector bundle. This, of course, if you restrict, then you still have it, and of course that you have. So locally, what you see is that the decomposition and the level of of cotangent bundle still exists. Our problem was to see if this passes to cohomology, since cohomology is more accessible than the bundles of forms. It's easier to compute cohomology than to compute forms. In fact, many problems of geometry boils down to this. For example, formal manifolds like Kähler manifolds are easier since all the information of the bundles is actually encoded by cohomology in some sense. And this is what we want. If we lose the Kähler condition, then this is no longer true. And so asking whether something which is what I will call a local property, so that that holds on the bundle, passes to cohomology.
Thanks.
This was
Are there any more questions or comments?
I have one little question.
Yes.
Okay, so well, thank you, Andrea, for the speaking. So it's about the definition of Dolbeault cohomology in almost complex manifold. You said that in almost complex manifolds we have four terms: del bar, mu, and mu bar. So the cohomology proposal by Wilson and the other one in 2021 is to do the cohomology with respect to the del bar operator to the cohomology defined in one of the other ones.
Yes, it's to start with the cohomology with respect to mu bar, and then to compute the cohomology with respect to del bar on this cohomology.
Okay.
So
And with
yes,
and with this cohomology defined, we can pass to the defining left chest operator, Hodge star operator, and try to compute in almost complex manifolds what we have in complex manifolds. I mean,
so I don't know, since the fact that, for example, the Lefschetz operator passes from the level of bundle to cohomology in the complex case is a consequence of the Kähler identities. Now, there is some paper about Kähler identities in the almost complex setting, but I don't know if this gives you the answer to your question. If you can use that relations to see that you can still define a Lefschetz operator at the level of Chirich and Wilson's Dolbeault cohomology.
Okay. Yeah, related to this, for example, in order to relate when the Hodge theorem is satisfied in non-Kähler geometry, for example, we have to look for what we call the Fröhlicher spectral sequence in complex manifolds. Do you know if Wilson-Dolbeault cohomology operator can we define another spectral sequence? Is there an analog of Fröhlicher spectral sequence in almost complex manifolds?
Well, I don't know if you have for that cohomology a Fröhlicher type spectral sequence. For sure, you have something, since manifolds satisfying the Delder-Bar lemma, for example, are known to have the Fröhlicher spectral sequence ending at the first page. That's true, but I don't know if you can move to this Chirich and Wilson's cohomology.
Okay. Thank you.
It's quite interesting that definition, in fact, but it's very difficult to deal with. Also to produce and to sketch some example and to compute it and to work with it. It's difficult. It's not so easy. The definition is quite easy, say not the easiest one, but then to work with it, it's actually a mess.
To work with it is so hard because you have
Yes.
a lot of. Okay, thank you. Grazie.
Prego.
Thank you. Are there any other questions or comments? Well, if this is not the case, thank you again, Andrea.
Thank you very much. Thanks.
Thanks, Andrea.
Thank you.
Thank everybody for come and see
Thank
you the
you.
next. Okay. Continue sending nice paper to the Revista.
Okay. Thank you. Thank you.
Everybody. Okay.
It's okay.
Bye.
Bye.
Bye, bye.
Bye-bye.
Bye.
Bye-bye.